Nice to be here. See all you young aspiring students getting ready to go out and do what you need to do, because there's a lot of people out there waiting for you. But there's a lot to learn, unfortunately, and this is just the beginning. I started at night 29 years ago, I believe. And yeah, haven't stopped researching. I listened to all these young gals and how they research. Well, it doesn't end. You keep on researching, because the more you know, the more you find out that you don't know. So I actually moved into a genetics area, which helped me learn some different things. But the basics that I learned at the Methylation Institute are what carries you into a new area of study. So that basic education is worth everything. And so I decided to give a little discourse on methylation. I did have a request to do something about RNA and its role in the COVID vaccine. So I kind of merged that. And so I changed my PowerPoint up a little bit to accommodate that. And so try to pay attention. It's a difficult process, but it's one that we all need to learn about, because that's where it's all going. So, methylation basics. And I have to learn how to use this little thing here.
You pushing the down arrow, the right arrow?
I'm pushing the front.
Try the other one. Try the other one. There we go.
So I'm going to try to give you a quick synopsis of what it is, what are the components, and what does it do. So, like Amy brought out, it's a chemical process that's complicated. But it adds methyl groups to DNA, to all the proteins that we use, that we learn about, and other molecules. Methyl groups are chemically inert, but adding them to a protein methylates them and changes how that protein behaves in major ways. So enzymes and hormones and genes are proteins, and the process of methylation profoundly affects them. So the word substrate is often used with methylation to the molecule that receives the methyl group. And I'll show you what that's about. Simply stated, the ability to transfer methyl groups by our cells by adding or removing groups as needed equates to cellular adaptability. So before you ate, after you ate, you are methylating in different ways. And you have to be adaptable. Those that aren't adaptable come to you with problems. In other words, a person who can methylate or demethylate appropriately will be healthier, because their cells are able to adapt to its constantly changing environment. Methylation reactions are fundamental to human metabolism, and examples include cellular detoxification, which is demethylating, neurotransmitter making, synthesis, making dopamine, cell growth, because our cells are always multiplying and dividing. They also have to repair, and it also provides gene expression. So the methylation process starts with a one-carbon metabolism. So if you ever look up methylation online or wherever, you're going to see something called the one-carbon metabolism. You're going to wonder, what is that? So it's one carbon with 3 hydrogen atoms. You see it up there in the corner. And it's inert. It does nothing unless you attach it in the proper spot to possibly a protein. In this case, it's cytosine. And when it was put in the proper spot at the 5 area, it became 5-methyl cytosine. So it changed the way cytosine works. Cytosine now is able to start DNA repair or DNA making. So the one carbon metabolism is a series of actions that looked real simple, but there's a lot involved, probably hundreds of things involved in one thing happening. But it moves carbon atoms from one compound to another in cells. It's a vital process that supports the cell function and survival by providing a methyl group for a variety of biological processes. We need to do all kinds of things. Our body's doing all kinds of things all the time, every minute. So the one carbon metabolism comprises a series of interlinking metabolic pathways that you've probably seen before. You've probably seen something called the methionine pathway, the folate pathway, the B12 pathway. You've probably seen these pathways, and they're made up of this one carbon metabolism that comes alive and changes how things flow through. So here's a couple pathways that I found. The one on the left is folate pathway. And folate is inert at first when you eat it. We just ate a salad. And of course, it's not methylated. It has to go through a process. The process, it's called methylation, of course, but it has to go through that second gene up there on the left, the DHF, and then the DHFR. And that, going through that process, will methylate folate into something useful called tetrahydrofolate. And tetrahydrofolate will then it's methylated to a degree, and then it changes into methyl tetrahydrofolate reductase at the end, the famous MTHFR gene. And then MTHFR enzyme ends up in the middle by the M, I think that's an MS up there, and starts the B12 pathway, which the two of them together then push the methionine pathway and make stannine, which is the end result of methylation. There is up here a pathway that goes down, which is the transsulfuration pathway, and that's a detox pathway. And you're methylating all the way through that detox pathway. If you can't methylate, you don't live. In fact, if you can't methylate, when you're in the womb, you die. You have to be able to methylate in order to stay alive. So there are more players needed for methylation. So the term methylated includes the one carbon metabolism plus methylfolate and methyl B12. And some of the things that are needed are B2. You can't methylate without B2. It's a cofactor. B6 can be a cofactor, not in every instance, but most of them. Choline is another one. When we're talking about lipid nanoparticles, think about choline. Choline from egg yolks is the best thing that you can do for your body. It's needed in methylation. It's needed for methylation in the brain. It's needed so you don't get Alzheimer's. And what do they tell people when their cholesterol is up? Yeah. Well, if you don't eat eggs, you can't methylate. And if you can't methylate, you know what happens. So iron is often needed, zinc is needed, magnesium is needed, and selenium. So we as naturopaths need to teach people and ourselves how to beat our methylation cycle. What things are needed, and are we giving our body the raw materials that it needs to make the product that we want it to make. Player number one, folate, needs an enzyme conversion process. Like I told you, when it goes in the mouth, it does not, it's not methylated. So the dihydrofolate will methylate it. Tetrahydrofolate is the result. L-methyl is the next result, and methylene tetrahydrofolate reductase is the end one. I just wanted to stick up here where products that you sell are involved. So tetrahydrofolate is where calcium folate would fall. 6-S-quadrifolate will fall in the L-methyl part, and the L-methylfolate part is methylated folate. Another picture of the methionine pathway. I do want you to, folate B12 pathway too. I do want you to pay attention to the pathway on the left there, the DTMP, the DUMP, pyrimidine synthesis, and purine synthesis. That's where the nanoparticles are formed. That's where the fats formed and added to the methyl group. So another picture of how folate is reduced all the way. There are a few other genes involved, but we don't have time for everything. Wish I did. We don't. So player number 2, B12, enters at multiple sites. It enters in the stomach if you're not taking anything for acid reflux. If you're taking something for acid reflux, that IF, intrinsic factor, is not allowed in. And so intrinsic factor is what takes the cobalamin to the liver. And intrinsic factor is like a Uber driver. Picks up cobalamin wherever it can find it. And as you can see, it's located all through the small intestine. Everywhere. It's like somebody's watching at the door for B12 to come in. Because you've got to grab it quick and send it to the liver because it's needed in so many areas. It used to be that they were saying that there's 36,000 enzyme reactions per second per cell, but now they're saying there's billions per second per cell. And this is the folate and B12 are the things that make that happen. So we see cobalamin going through the small bowel, and we see intrinsic factor everywhere trying to pick it up. And of course, the brush border is the main place for that to happen. Now, some of the B12 goes one way and some go another way. I'll show you that in a minute. So cyanocobalamin, there's 4 types of B12, and I'll tell you where they go. But cyanocobalamin is the one that they've used for years and years and years. And cobalamin isn't by itself in nature. It doesn't live by itself in nature. You have to, it's got to be a compound. It's got to be attached to something for you to actually look at it or take it as a pill. So cyanocobalamin was what they used forever and ever. And that's, of course, cobalamin hooked to a cyanide molecule. And so the absorption rate on that is about 12%. It's slow moving, and it does bear some toxicity as well. So it has to be cleaved by the liver, which takes quite a long time. And for 12%, it's not really that great. That's why they give you shots, because they give you mass amounts so that some of it will go where it needs to go. Hydroxycobalamin is most of the B12 found in food. So beef, chicken, turkey, eggs, and yeah, most of the meats and things are full of hydroxycobalamin. Adenosocobalamin is a convert. It's converted from hydroxy via transcobalamin, which is a gene. And there's transcobalamin 1, which works outside the cell, and transcobalamin 2, which works inside the cell and is allowed inside the mitochondria to perform the methylation magic. Methylcobalamin is jumping all the hoops and jumping right up to the methylation process. Now, we used to think this was really good because it makes you feel real good right away. But we found out that it might not be as good as it sounds. Because you're going to speed up reactions that are good and bad. So if you need to cut down on methylation because the people that that are coming to see you are overexcited, they can't sleep at night, their asthma's starting to bother them. They felt really good at first, but now they just got all this going on and you just can't shut them down. What do you need to do? Well, you might want to use a different form of B12 for them, because I wouldn't choose cyanocobalamin, but it is an option. Hydroxyl and adenosine, neither one of them are methylated. Now, some people have a hard time methylating, because transcobalamin 1 and 2, even though it's an adenosine cobalamin and helps with muscle tissue, wonderful, gives you more energy. Methyl is used for DNA repair, for neurotransmitter making, all that type of thing. But if, I lost my thought. Anybody remember it? So you can switch off to another type of B12 if you're finding that the methyl B12 is not working for them. But some people can't methylate well because their transcobalamin does not work, and it doesn't break it down to the methylation process. That was my thought. And so methylation is good, helping them methylate is good. But because this stuff it can't be tested on everybody because we're all different. We all have different breaks in our DNA. We all have, we're all different, completely different. I could never believe it until I saw these people coming in with all these different genes with different, breaks. Some totally mutated, some partially mutated, some green, and it's all over the place. So when they take a methylated product, those genes that don't work very well are really going to work, and some of the ones you might not want them to work that well. We want them to have neurotransmitters, but remember, if you give them a methylated product, they're also going to degrade them faster because you're speeding it up. So you're giving them more serotonin and you're getting rid of it as fast as it's being made. So is that good or bad? You have to think about it. And every person's different, so you have to decide how much, when, because there's no studies. You can't do a study on this. So increased detoxification can be a problem, and let's say they have a BRCA gene. You can speed that up and breast cancer speeds up. We don't want the BRCA gene to be methylated. So you have to think in terms of those types of things. A small amount of methylation every day might not be a bad thing at all. But to be totally on a methylated product without giving any of the others might not be the best way to go. So changes in methylation have been associated with negative health problems, and if we start smoking, or we're drinking too much, or we have heavy metals, those types of things, we can also slow down methylation and create a problem as well. So lifestyle changes definitely have an impact on methylation patterns. And I put that date there because this is brand new stuff. So we're just learning all this stuff. There's some medications that will interfere with either folate, B12, or B2, B6, some of those things. Anti-seizure medications, chemotherapy, particularly methotrexate. One chemo agent that I was to receive in hospital, 5FU, works the same place where the vaccine is being utilized, which I thought was interesting. So I learned some things. H2 blockers, we know because we need stomach acid. We need to digest our food. And if we don't have stomach acid, we don't have intrinsic factor because we're stopping, we're blocking. Metformin also, glucophage taken for diabetes, works at the cellular level, at the transcobalamin area. Proton pump inhibitors work in the stomach to reduce stomach acid, so no intrinsic factor is there. Birth control pills, steel, B12. Menopausal women have shown an association between low B12 levels and low bone mineral density and the meds to correct them. Meds that interfere are also the RNA vaccine. Let's talk about it. The pharmaceutical intervention for the RNA vaccine is right there in the corner by the TYMS gene. That gene is a thymidylline gene, and it has the part of the important job of translating uracil, RNA uracil, to thymine DNA. I'll show you that. And plus, that area right there is rich with lipid nanoparticles. I showed you that earlier and told you to remember it. So RNA contains a uracil in place of a DNA thymine, and it looks like it's half done, or like a half helix there. And on the right side, we have full DNA. Uracil needs to be converted because it can cause mutations and genomic instability in DNA. Imagine that. It has to be converted. It can mispair with U and G. The base excision, the repair mechanism, works one time, just once. If it can't work that time, or it doesn't work that time, or it does work that time, the next time it doesn't work. That leads to DNA strand break, gene deletions, chromosomal breakage. This is the area that the RNA vaccines excel. They love this area because there's something there called pseudouridine, the most abundant RNA modification. Pseudouridine is an isomer of uridine in which the nitrogen-carbon glycosidic bond of uridine is replaced by a carbon-carbon bond. I know that's over your head and hard to understand, but that's what happens. And so because of that, they use something to trick the body. They use something called nitrogen 1 methyl pseudouridine, which is man-made, like we can make methylfolate, we can make methyl B12, they can make this. A methylated derivative of pseudouridine, and is usually used for the mRNA vaccines, and here's a picture of it. So here we have a picture of normal uridine. We have a picture of the pseudouridine, which is in process to becoming thymine. And that's where they jump on the bandwagon and they stick that nitrogen and the one carbon metabolism in that place and then methylate that thing. And the article that I got this from, I'll give you it, they admit this.
So in layman's terms, Dr. Featherly, what does that mean for us? Our DNA can't repair itself? What does it mean in layman's terms?
Your cell has one chance to repair itself before it becomes thymidine, before it enters. How many vaccines do they want you to get?
So the end result is our DNA cannot repair itself, our DNA changes?
The DNA doesn't recognize it at all. Because this is the trick that they pulled. So here's a picture of it. So here we have the lipid nanoparticles, called acutis, by the way, and I would look that up. We have an unmodified mRNA encoding spike protein, the J&J vaccine, on the left. And as it gets injected and the host cell decides to make an antibody against it, the unmodified J&J vaccine has a lower efficacy, 48%. They didn't tell you you had to have a second shot on that one because it's the old way. They put it in raw. The right side N1-methyl pseudo-uridine modified mRNA encoding spike protein, and this is the picture that they put in the article. That a uridine now has an N-methyl group, and it gets to enter the DNA like that. And modified vaccine has a higher efficacy, 90%. So, that's what I found out. And I can see, this is the last slide.
Dr. Featherly, does that mean, so what you're saying is that they're methylating to speed up the process, there's a break in the DNA that we can never repair that DNA because of it being methylated? Is that
That's correct. It's that simple. But there's a lot of processes in between, but I tried to make it as simple as I could. So, the novel coronavirus, SARS, this is a quote from their word. SARS-CoV-2, the cause of COVID-19 pandemic, has inspired one of the most efficient vaccine development campaigns in human history. A key aspect of COVID-19 mRNA vaccines is to use the modified nucleobase and 1-methyl pseudo-uridine to increase their effectiveness. Isn't that cool? But by demystifying how a novel element within these medicines work, we aim to foster understanding and highlight future opportunities for chemical innovation. And that's the article. So I've started a study group called Jackie's Study Group at yahoo.com where we investigate more stuff. And I tell you more about genetics. So if you're interested, let me know.
Can I ask you one more question, please?
Certainly.
So if we've already have a break in the DNA, and then we, as a person, give methylated B12, we're not really harming them anymore because it's already broken, correct? Or are we speeding up another process?
All the processes in the body are methylated. Every protein is methylated. Body processes are all methylated. This is just part of the way our body operates that we didn't know about. Back when I started school, this wasn't even, it wasn't even out there, but they'd taken the human genome apart. And they found these things out. And they're learning by leaps and bounds, as you can see, what to do and how to do it better and better and better. It's getting dangerous. Sometimes I think it might be too dangerous to be alive. I don't know. But yeah, so this is just a body process. But it's something that naturopaths need to know about so they can see the signs of maybe too much methylation or not enough. So somebody comes into you with breast cancer, do you want to give them methylfolate? Probably not. You probably want to give them a calcium folate because they still need to methylate, but you don't want to speed it up.
Okay.
So just some things to think about. Folate comes in the methylated version, and so does B12 come in the methylated version. A little bit of methylated B12 is needed by the body. You need some. So make sure if people come to you with serious symptoms that are out of control, really fast, which corresponds to the syphilis miasm, that you tone down the methylation, the B12 methylation. And you can try a methylated folate to see if they feel better. If they feel better on methylated folate, they may need one. There's another gene called the SHMT1 gene, and that gene, if it doesn't work, needs some methylfolate. So, food for thought. Go do your research. That's what you do good.